Joy, Vice Principal, Deans, Alumni Office bearers, and all my colleagues in the college to this webinar. We have nearly
Thank you.
yeah, we have nearly 500 participants registered for the seminar. I think more participants will be joining to the seminar in short time. I thank you all for your support. I extend a very warm welcome to all the participants, including past and present students of this college, especially the students of physics and chemistry department, all the faculty members, research scholars, postdocs, and other general public who are joining from different parts of the country and the world. Wishing you all a very enlightening and engaging session. I welcome our principal, Reverend Father Jolie Andrews, for his message. Yes, Father.
Okay. Okay. Am I clear and visible?
Yes, sir.
Thank you. Thank you. Professor Pulickel M Ajayan from the Rice University of United States of America, one of our prestigious alumnus who will be delivering the talk today, the impact of nanotechnology. As we all know, he is one of the pioneers in this field. I would say giant in this field. Dr. K.Y. Shaju, the Vice Principal and HOD of Physics. Dr. Joy V.T., the HOD of Chemistry and the Research Coordinator. Father Joy P.T., the Vice Principal. Dr. C.O. Joshi, the Vice Principal. Dr. Tessie Paul, the Dean of Science. Dr. Aravinda B.P., the Dean of Humanity. The Organizing Secretary, Dr. Sudhir Sebastian K. The Organizing Secretary is also the Secretary of our Alumni Association. The Executive Committee members, Sri Jason Parakadan, the Vice President, Sri P.A. Jose, the Joint Secretary, and all the members of the Alumni Association, respected faculty members, the researchers from the different parts of the globe who will be joining today. Indeed, today is a very prestigious moment for the Christ College to have one of our alumnus, Dr. Ajay Pulickel, who I would say you already know is one of the giant of this field, one of the pioneers of this field, who has contributed immersely in this field, who will be talking to us about the impact of this nanotechnology in this present scenario. So I'm very happy to have Dr. Ajay Pulickel, who also hails from our nearby locality in the Kodingalur and who has studied here in the Christ College, who will be presenting this paper. I would just want to say that he has got around more than 1 lakh citations with an H index of 155. It is one of the remarkable feat, I would say, regarding any researcher, I would say. Having a journals of more than 1,000, around 1,100 journal papers means the huge volume of the work which I have done really speaks about it. So I'm very happy to have him here, and we are also very blessed to have him here, especially to have this webinar that has been organized, jointly organized by the Alumni department of the Christ College, the Department of Physics and Department of Chemistry. So before we start the webinar, I would like to make a few facts about our college. Our college was started in 1956 by the Devamada Provincial Carmelites of Mary Immaculate. It's the first indigenous religious congregation that was founded in 1831 by St. Kuriakos Elias Chavra, a saintly priest and a versatile genius. And the college is re-accredited by NAC with the highest grade A and has been dedicated to Christ and has as its motto Jivida Prabha, which means light of life. The college has become one of the prominent epicenters of academic training in the country, thanks to the visionary leadership given to it by its first principal, Padma Bhushan, Father Gabriel. colleges at present 27 UG programs, 16 postgraduate, and 11 departments are offering PhDs. 11 departments are having guides who are offering PhDs, and also 21 certificate programs. And at present, around 3,860 students, that is the status of the last year. Perhaps the largest number of students are now studying in our college. The college has also entered MOUs with the University of Zululand, South Africa, and the Leibniz Institute for the Applied Geophysics from Germany. And in this happy notation, I would like to speak about a few words about the Alumni Association, which has been a registered trust now. And I appreciate very much the organizing secretary today, Dr. Sudhir Sebastian, who has done all the work in organizing our alumni in a wonderful manner. And it is because of his initiation, I would say, we have realized this wonderful seminar here under Dr. Ajay Pulickel, who would be speaking to us just now. So we have also, the alumni is also organized in different wings. We have got a department alumni, physics has got a pack, and a lot many students have joined to it, especially to the initiation of our beloved HOD and Vice Principal Dr. K.Y. Shaju. And in the research scenario also, we are moving very forward in our own way, in our own pace. And we have got our Dr. Joy Beatty, who is wonderfully organized. Who will be wonderfully organizing all the research activities of our college. And we have got Jason Parakadan and the distinguished alumni office bearers of our college who are also attending this webinar, who has come forward in order to make this webinar a wonderful possibility. So I'm very happy to have this blessed day. I'm very happy to have our beloved Ajay Pulickel sir with us, and he has promised that one day he will really actually come here once this COVID is over. So let us really enjoy the nanotechnology, and we are going to really enjoy this nanotechnology as we're attending to one of the pioneers in this field, Dr. Ajay Pulickel. So have a wonderful day, have a wonderful webinar. May I remain. Thank you very much.
Thank you.
Thank you.
Can I share my screen?
Now I invite, 1 minute, sir. Now I invite our research coordinator and HOD chemistry, Professor V.T. Joy, to introduce, to give more details. Joy, sir, please.
Okay. I feel privileged to introduce Professor Aayan M Pulickel. He is the Benjamin M. and Mary Greenwood Anderson Professor of Engineering at Rice University and founding chair of Department of Material Science and Nanoengineering. He is a pioneer in the area of nanotechnology. He has published more than 1,100 journal papers, earning more than 100,000 citations and H index of 155. His work covers diverse areas of nanomaterials, including nanoparticles, nanotubes, 2D materials, nanocomposite, and energy storage materials. He is a recipient of several awards such as Spears Memorial Award, Alexander von Humboldt-Helmholtz Senior Award, and Lifetime Nanotechnology Award from Houston Technology Center. We are very proud to note that he did his pre-university studies here in Christ College, Irinjalakuda, in the period 1978 to 1980. He obtained BTech degree from Banaras in the University of Varanasi, India, in the field of metallurgical engineering in 1985. Then he obtained PhD from Northwestern University, USA, in material science and engineering in 1989. After that, he did 3 postdocs, one in NAC, Tsukuba, Japan, and second in University of Paris, France, and third in Max Planck Institute, Germany. With this introduction, let me welcome Professor Aayan M Pulickel to this international webinar to deliver a talk on the topic Impact of Nanotechnology. I welcome you, sir.
Thank you very much. You can hear me, right?
Yes.
Yes, yes.
Let me share my screen. Can you see the screen now?
Yes.
Yes, yes.
Yes, sir.
Okay, let me first thank Christ College for inviting me, and Dr. Jolie Andrews, who's the principal, for the kind words, and the faculty and the students. I hope you will take something away from my webinar today. I'm going to keep it reasonably broad so that people from multiple disciplines can get some information. But before I go into my webinar, let me say a few things. As it was already mentioned, I'm a native of Kodungalur, which is not that far from Christ College. 40 years ago, I was a student at Christ College. Although it was that long time ago, the memories are still very vivid. I used to take a bus almost every day from Kodungalur to Iringalakuda and get down in Christ College. In fact, it's interesting. There were several days when there was a strike in the college, and we used to just hang around the campus of Christ College and enjoy the place. I'm sure that things have changed. And as I was telling Sudhir, I will certainly come and visit Christ College next time I'm home. I do come once in a while, at least once a year. So, again, I'm very, very happy to give this lecture. And when Sudhir reached out to me, I didn't even think about whether to do it or not. I was immediately happy to do it. So hopefully, this will be the start of some relationship between Christ College and our university here. So what you're seeing in the slide is actually RISE, the original buildings of RISE. RISE is actually a 105-year-old university. It's one of the gems in the southern part of the United States. It's in the state of Texas. In Houston, I don't know how many of you know, it's the energy capital. Most of the oil and gas companies have their headquarters in Houston. So it's a big mega city with a population of about 6-7 million people. And RISE actually is in the center of the city of Houston. And it's not a very big university if you compare with some of the major universities in the US. In terms of size, we have about 6,000 students in total. Out of that, about 4,000 are undergraduates and 2,000 graduate students. And we do provide a large range of disciplines in education. We don't have a medical school, we don't have a law school, but most of the other schools are here. And I'm from the engineering school and from the Department of Material Science and Nano Engineering, which is one of the most recent departments in the School of Engineering. And as it was mentioned, I was the founding chair of this department. Now, again, as I said, this talk is going to be quite broad, and at least to introduce you to this whole area of nanotechnology. I've been working on this for almost 25 years now. At least give my impressions and more the impact of what this technology can bring to our lives. That's basically the message that I would like to give. Now, let me start by quoting one of the popular premier physicists of the century, Michio Kaku. He says, by 2100, our destiny is to become like the gods we once worshipped and feared. But our tools will not be the magic wands and potions, but the science of computers, nanotechnology, artificial intelligence, biotechnology, and most of all, quantum theory. Some of these things you probably have already heard. I mean, obviously, computers we all use, and we can't live without computers. Biotechnology is very obvious and very relevant today. And again, you might have heard of things like artificial intelligence, which is pervading through many fields of science and technology today. Of course, the quantum theory, quantum materials, and quantum technologies are really going to be the most revolutionary kind of technologies that are emerging in many different ways. But I particularly wanted to pick out that word nanotechnology. In Kaku's words, he clearly says nanotechnology has a place in the future generation of technologies that are going to change the world. So that's the topic today. I mean, it may not be very obvious why nanotechnology, which is essentially based on a length scale, nano essentially length scale, should have such an impact. Hope that things will become clearer as I give you some examples and some relevance for this particular technology. So let me, given that, as I already said, it's a length-based technology, essentially materials and devices that have sizes in the nano scale. So just to illustrate how small is nano, I picked up a demonstration. So what you're seeing in the slide is a cube of material, let's say 1 centimeter cube, surface area of 6 centimeters square. And what if you, start to break up this cube into smaller and smaller cubes? So if you take this material without actually removing any matter, the matter is constant here. The volume, obviously we will see. But if I'm going to break this into smaller cubes of, let's say, 1 millimeter cube, I will end up with a surface area of 60 centimeters square. But if I were able to really break it down to 1 nanometer cubes, right, your surface area becomes 6 crore. I mean, it's a humongous number, right? So what is essentially happening is that as I'm breaking down this block of mass into smaller and smaller pieces, essentially the atoms that are sitting in these cubes are not anymore bulk atoms as you would see in the original cube. Many of them are now surface atoms. The surface area has increased enormously. So the way to handle, although it's the same amount of material, the way you would handle a cube of 1 centimeter and that humongous mass of, the broken down material is quite different. And there are challenges and opportunities in this particular field simply because of the way we have transformed matter as you break it down from a macro scale to a nanoscale. This kind of comes out in almost every area of nanotechnology that we work on, whether it is electronic devices or whether it is nano composite material. This large surface area, this large interfacial area that it provides actually has an enormous impact on the way materials behave. And now I also want to say that this is the kind of approach, at least one approach that people have taken to create nanomaterials. I would like to call it a top-down fabrication. You essentially machine down things, all the way to the smaller scale. Machining is something we all know, we are all familiar with. But of course, when you machine down things to the nanoscale, things are quite different and quite complicated. In fact, the entire computer industry works on this top-down fabrication approach. You might have heard of lithography, right? And I'll later on mention the level of sophistication that you have in lithography these days. But top-down fabrication is simply the approach that most of the industry takes today in terms of creating nanoscale object, nanostructures, and understanding these. There is another approach that one could possibly take, and that is what I would generally call bottom-up fabrication. And bottom-up fabrication is interesting because a lot of our biological systems have been created through bottom-up fabrication. Most of the membranes and cells and DNA, all the way down to the DNA, they've all been assembled from bottom up, from single molecular units to larger functional structures. This bottom-up approach has been very, very important and relevant in biological systems. But from synthetic technology point of view, bottom-up fabrication has not really reached the sophistication that the top-down fabrication has reached. When I say bottom-up fabrication, one could think about going all the way to the atomic level. How do I manipulate single atoms and start building larger structures that provide certain types of functions? This is a classic example of the image that you see here, published from the IBM Zurich group many, many years ago, on what they call the quantum quarrel. Essentially, what they did was they used an STM, scanning tunneling microscopy tip, to actually push atoms around and build this, this circular geometry of atoms, which essentially creates a standing wave pattern, and it's got some interesting quantum behavior. So this is kind of the ultimate, bottom-up fabricated nanostructures we want to build. But today we are not really in a position to build that because it's quite complex. Picking up atoms one by one and putting it in place and building structures, you can imagine it's not a very scalable approach, and it will have interesting challenges. But there are certain things where you can do bottom-up fabrication. For example, you can assemble a cluster in a solution, or you can actually create a structure that is nanoscale in vapor phase. So I'll show you some examples of that. So just as an introduction, I want you to be clear about what the world is doing in nanotechnology in terms of creating nanostructures, the top-down and the bottom-up. These are two competing approaches. And one day I imagine, that the bottom-up fabrication would be at a stage where we can actually build realistic structures from single atoms. I think that people actually say that nanotechnology in its long term is essentially, single atom based manufacturing, right? So if you can have control on every atom that you place in a structure, then you have enormous flexibility of defining the functionality of these structures. So that's where the nanotechnology becomes so powerful. And let me give you a few examples of some of these heroes of nanotechnology in terms of materials. These are essentially the poster children that has really fascinated people over the years. The carbon-60, called the fullerenes. Again, I'm assuming that people have seen a few things here and there. This is, again, a discovery that was made at Rice University, received the Nobel Prize in Chemistry in 1996. This is probably one of the early structures that defined the pathway for nanotechnology. And it's a beautiful structure, 60 atom carbon that is organized in what is called an icosahedral symmetry. It's got almost exactly the structure of a soccer ball, and that's why people call them soccerenes and all kinds of things. It's actually called fullerenes because the Buckminster Fuller, who was an architect, he used to build buildings, they called it geodesic domes, based on these type of symmetry. So when the fullerenes were discovered, there was some correlation between those, and people started to call them fullerenes. But anyway, I mean, this is one of the examples of how precisely controlled number of atoms can be coaxed into really a beautiful structure, and you can make them in large quantities and so on and so forth. Again, application-wise, I mean, people are now using this for dye-sensitized solar cells and drug deliveries and things like that. But it's a beautiful molecule. It's got a cage-like structure, which is really a beauty. Another exciting structure that has captured the imagination of people recently is the graphene. Again, the same material. The fullerenes were also made of pure carbon. Graphene is even simpler in its structure because we have all used graphite some way or the other. In the pencils that you use, you have graphite as a composite. So graphitic structures are interesting because they are very anisotropic. They have very strong in-plane bonding and very weak van der Waals forces that keep these layers together. In the early 2000s, people realized that there are ways you can simply exfoliate each layer by layer, and then explore the properties of a single atomic layer of carbon. And again, that received the Nobel Prize in Physics. Again, it's a very simple structure, but what was interesting is that once they were able to extract a single layer, they could find really fascinating physics in these layers, single atomic layers. And I'll talk a little bit later on single atomic layer materials. There are some similar kind of structures, but I wanted to show this one particularly, carbon nanotubes, because I've worked quite a bit on this. But again, the structure of carbon nanotube is really fascinating. Same structure that you saw in the graphene layer, but what you do is you take the graphene layer, which is a two-dimensional layer, almost like a paper, and then you fold it into a straw. gives you this nanotube. But why is nanotube so interesting? I mean, one of the reasons why it is so interesting is that small changes in the structure. For example, you can see if you follow the hexagons in this picture, there is some level of a structural attribute which is called chirality or helicity. You can see these hexagons winding around the tube along the axis of the tube, right? So again, by the folding of this layer, you can change the chirality of the structure, and depending on the chirality and the size, which is again in the nanometers, people understood early on that the electronic properties are different depending on how exactly the structure is formed. So that really, again, was one of the early starting points of nanotechnology, where people realized that small tweaking or small changes in the structure and dimensions when things are at the nanoscale can significantly change the electronic properties. So carbon, this whole material is made of carbon, right? Carbon is essentially, or graphite is a semi-metal. But by doing this kind of structural engineering at the nanoscale, you can go from metallic to semiconducting material, even from pure carbon. So it's an ingenuity that you can bring in at the nanoscale by simple structural modifications that can change the entire electronic properties or physical properties in general, that really made nanotechnology so exciting from a structural point of view. So, again, people have done all kinds of things in terms of tweaking the structure, figuring out how you can make these into electronic devices and so on and so forth. Again, I don't have the time today to go into that. But again, this is another beautiful example of how the structure property correlation gets strongly implemented at the nanoscale. And of course, people have imagination. Research is all about knowledge and protocols and imagination. And people, there are like Richard Smalley, who actually received the Nobel Prize in Chemistry for the discovery of fluorines. He was from Rice. He's no more. But he would say things like, yeah, these nanotubes are lovely. They are one of the strongest fibers at the nanoscale. But I would like to spin it and make a very long fiber so that I can make a space elevator. Right? Again, I think it's a very interesting statement that that you can think about, an extremely strong fiber that would be used in something like a space elevator. And a space elevator, I don't know, again, if you have heard about this, it was part of science fiction for a long time. And, idea is to have a very, very long cable coming, all the way to space. But the problem with such a thing is that most materials would creep and fail by its own weight if it is that long. And carbon, because of its very strong carbon-carbon bond, is perhaps one of the few materials that can be made into such a long cable and still would be strong and will not fail. But again, that question about whether you can make such a long cable from starting from nanomaterial is really a loaded question. It's very, very challenging. It's extremely difficult, because you can imagine, when you might have very strong and very interesting properties at the nanoscale, but as you start putting these things together into a macro scale structure, you start compromising on properties because of all the interfaces that you bring in. So even today, this statement was made maybe 20 years ago. Even today, people have not been able to really make that kind of a long cable with that kind of mechanical properties. But I should say that enormous progress has been made. Here is a colleague of mine from Rice who now spins carbon nanotubes into really long, fibers and cables for all kinds of applications. I mean, imagine a ton of applications. You could even be replacing copper wires. Metallic wires have always problems. So if you can make a carbon fiber or carbon wire that is long enough and with good mechanical and electrical properties, you can really bring major innovations into electrical industry. And then there are, the whole concept of what type of innovations is happening in materials and devices. End of the day, I already mentioned once about the biological systems. The reason Biological systems are interesting is because they have properties that we cannot really emulate in the synthetic world. You know, for example, you can break your bone, but after a while, the bone will heal itself. You know, you don't have a material that if you break it, I mean, will heal itself, right? I mean, ultimately, that is the goal. What we want to make are materials that would have all these, you know, intrinsic properties for, you know, long-term performance. I mean, again, biological systems are perfect for this because they're complex. You know, they can sense, they can self-heal, they can do all kinds of things. So in terms of the material science and engineering, the long-term perspective is for us to kind of think about these type of smart, intelligent materials, not specifically in one field only. I mean, in this particular code, again, you're talking about some mechanical properties, but it could be, you know, in all kinds of properties. Artificial intelligence essentially is trying to, you know, help in this regard, essentially getting a lot of data and analyze data so that you can drive the system towards some positive outcomes. All right. Of course, it involves a lot of data analysis, but nevertheless, you know, combination of materials and data, one day one might be able to, you know, do a lot of things with these innovations in not just material science, but also in things like machine learning and so on. So again, multifunctionality is another part that is essentially embedded in nature, natural materials. And we are just beginning to see that. I mean, for example, I can imagine that, you know, the components of a structure itself would be useful for generating power. And let's say that you have a carbon fiber based concrete or something like that. And the carbon fiber could be electrodes for a battery. So, you know, there could be power that is embedded in the structure itself. And that would enable a lot more you know, intelligence to be built into these structures. For example, let's say you can have sensors that are powered by these kind of devices. So again, another concept that is emerging in many of the material science area is to be able to create multifunctionality. All right, how do I create a structure that is not just good for one thing, but for multiple things? And this is again perfectly in synergy with materials in nature. You know, natural materials, most of them are multifunctional. I mean, talking about natural materials, you know, nanotechnology manifests itself very strongly in materials that you can find all around. Of course, you know, on the beaches of Kerala, you can find these type of conch. That. And that's a, you know, a beautiful example of a nanoscale engineering or nanoscale engineered structures. And what you're seeing here is actually a calcium carbonate. 99% of this material is calcium carbonate. Calcium carbonate is another form of calcium carbonate is chalk, right? Chalk that you use on the board. And it's so brittle, right? It's almost exactly the same material. Of course, you know, what is different here is that the calcium carbonate has now been synthesized into extremely thin platelets, almost at the nanoscale, and they are sandwiched between protein layers or polymer layers, or, you know, organic matter. And this particular brick and mortar kind of engineering gives it the toughness that it has. I mean, for example, it's very, very difficult to break something like this, right? Because it's extremely tough. I mean, if you start, you know, creating cracks, then the cracks would deflect and the large amount of energy will be absorbed. So it's not easy to crack something like this, but almost the same material, chalk, you can easily break it in your hand, right? So the same material, if you can package it through nano engineering, nanoscale engineering, you can get a material that is completely different. Another example that you see in Kerala all the time is the geckos, right? The lizards. And again, there is a nanotechnology, you know, factor here. I mean, I don't know how many of you have wondered how the lizard actually stick on the wall or, you know, go upside down on your. It is not because it is creating some suction or something, simply because the feet of the gecko has extremely tiny fibrils, which are almost 100 nanometers or so, submicron range. And when they press their feet against the wall, you know, all these things come in contact with the wall, and the enormous van der Waals forces that exist during this contact allows it to actually, stick on the wall. So today there are many, many people, including our groups, we have done some work in this area, trying to mimic this type of structures so that you can have, these gecko-like layers that could be useful for climbing walls and things like that, vertical climb. So again, nanotechnology is in nature, and if you analyze many of the natural structures and objects, you can see this relevance between how nature has evolved to figure out certain things through nanoengineering. So I thought it would be interesting to show a couple of these slides. And in terms of technology, that is what is really driving most of the investments and innovations. Where are we? I mean, if you electronics and computer technologies are the easiest one to look at. And today, if you look at the computer chips, the basic device structures, the next generation would be close to 7 nanometers in dimensions. So the silicon devices that you might find in your computer chips, 10 years or 15 years from now, the components would be in that range, 7 nanometers. That's really very, very, very small. DNA is about 2.5 nanometers. Your hair, strand of hair is probably 100 microns, several orders of magnitude larger. So the semiconductor industry, again, through this bottom-up approach, have really pushed the limits of what they can do in terms of fabrication. And now they are working, at the 7 nanometer, or even, sometimes they even talk about 4 nanometer, but that's probably in the next generation. Today, if you look at the computer, you use, the chips will have, things in the range of 20 nanometers to 50 nanometers device range. So they have really figured out how to, manufacture in large scales these kind of materials with those kind of dimensions, and still, work robustly for a large number of device performance cycles. So that's really the amazing thing about technology, right? I mean, understanding is the scientific aspect, but technology is slightly different because they have to really have consistency. They need to have scalability, low cost, and I think the semiconductor industry has done an amazing job of doing this. Now, let me very quickly go through a few things that we have done in our lab. And again, nanotechnology is a big area, and one talk is not really we have actually entire courses devoted to different aspects of nanotechnology. But let me, I think, given that I'm talking about things that we have done, I would like to show a few things, especially the challenges and opportunities in this area. So one of the things that, that is very challenging is the assembly of materials. And I already mentioned this briefly before. It's not easy to pick and place things one by one to build larger structures. That will take forever, and that is not really a scalable process. So we need to figure out ways that you can assemble large number of these structures so that you can build macro scale structures. So it's something like a Lego, right, game. So that when you were young, some of you must have played this game. Essentially you have these pieces, and you're putting these pieces together to build various structures and forms. The only difference is that when you're doing the nanotechnology game, these Lego pieces are kind of invisible. So you cannot really, hand in place. You need to have something like a scanning probe or something to push things around. But even that is, as I said, not very feasible because of the scalability aspect. So you need to really, have some tricks up your sleeve to really figure out how you can assemble material. And here is an example. This is a simple vapor deposition technique that we developed in our lab, where you can assemble millions of carbon nanotubes, in a vertical array configuration on a. Again, I don't have time for the details, but this is indeed. And if you can do that, then you can really get some fascinating properties out of these aggregated structures, these aligned structures of nanotubes. And one of the things that we did a long time ago, actually this came in the Guinness Book of World Records, in making an array of nanotube that would make the darkest material that has ever been made. When dark material, it means that it absorbs a lot of light. Pretty much all the light that goes in doesn't reflect, doesn't transmit. So these arrays of nanotubes got into the Guinness Book of World Record. You can see myself and a postdoc of mine holding a piece of this carbon nanotube film, which was actually evaluated as really super dark. And now there are a lot of people working in this area, including there are art installations, by famous artists who have used carbon nanotubes to create the blackest paintings and so on. So I think this was kind of a beginning of something that was interesting between art and science. Now there are also other ways of aligning structures, but assembly in general is a complex problem, and people have worked hard in using multidisciplinary techniques to be able to get structures that are ordered. This is another example of a film of nanotubes that we have made in recent times, which is almost 99% of the tubes are aligned in one direction. So you can imagine, right? A single nanotube is about 1 nanometer in diameter, right? And if you have billions of nanotubes and you want to align all of them along certain direction to make a film, and of course those films have some very interesting optical properties, that's really a challenging problem. And again, this assembly forms the core challenge in nanotechnology, right? Especially when it is a bottom-up approach. Of course, you can see that this is bottom-up, right? You have these large number of nanotubes and you're trying to assemble them in certain ways. The top-down, again, has challenges because top-down, the instrumentation that you have available today doesn't really allow you to go to extremely small feature sizes. So beyond 7 nanometer, they really have a problem in terms of going even further down. So miniaturization from top-down kind of stops at that point. So you need to kind of come back with this bottom-up approach. So that's why bottom-up, which is essentially molecular design and engineering, is very, very important. Now, there is even a bigger problem if you want to create 3-dimensional architectures like this. How do I really create these junctions and so on between nanostructures so that I can get certain types of, or something like more complex. These are some of the predicted structures, theoretically predicted, but if you start thinking about how to build these, that becomes really a complex problem. We have done some work in trying to use certain catalytic material to create junctions, and you can see that you could build some larger volume objects using these approaches. But again, these are very preliminary steps towards creating those beautiful structures that I already showed you. And then there is also this whole field of metrology, right? You could create something even at the nanoscale, but how do you really measure properties of these things? It's a complex problem, right? How do I measure the mechanical property of a single nanotube? You can make a prediction, but how do you measure and prove that this is the case? So again, this is another field of talk, but there are lots of instrumentation development that has happened in this field that allows you to do in situ diagnostics, in situ metrology, and also find how things behave. What you're seeing here in this complex image is that you can go with a tip and press on a nanotube in one location, and you can get a stress strain curve that is plotted. And at the same time, you can observe this through the microscope, right? So again, these are extremely complex instrumentation, expensive instrumentation, but any major center with nanotechnology would have some of these techniques that you can use to understand behavior at the nanoscale. And again, here is another example of graphene-based 3-dimensional structures. There are, if you're not worried about going to all the way to the nanoscale, there are ways today to make complex structures. And maybe some of you have already done this. Maybe your labs have these 3D printing. This is a very common technique that everybody uses. You can build very complex structures using 3D printing, even larger structures. But of course, the resolution is not good enough to go to the nanoscale. So again, if you want to build nano-based architectures, 3D printing is still far from the technique that you want to use. Now, interface chemistry is very important because, if I were to build larger structures from nanoscale objects, how do I connect them? If you think about the Lego pieces, you have these features that fits into each other when you put together two pieces of Lego. But when you have materials, I mean, that is, nanotubes or clusters, you don't have this, this facility. How do you bring them together? How do you put them together? So then you have to think about chemistry, right? How do I change the surface chemistry of each of these particles so that when you put them together, there is some attachment and then they form the, people call it directed assembly, so that, the chemistry is used to direct one object to the other and couple them. And again, there are multiple ways of doing this, but this is an interesting, and again, I'll skip a few slides given the time. Here is an example. Actually, it's a work that is taken from Professor Pradeep at IIT Chennai. He's a good friend of mine. I mean, his work deals with clusters. Again, different material may be made of ceramics and metals, but the same issue arises. How do you really assemble them? So you need to have these ligands that are connected to these clusters. And then when you put these things together, the ligands come together and then form this macro structure with clusters in the core and the ligands outside, and the ligands are connected. So the point I'm trying to make is, nanomaterials could be made. I mean, of course, it is still not so easy to make size-selected clusters and size-selected structures, but you could, to some extent, make it. But assembling them in certain configurations and making functional materials out of these, it could be quite a challenging business. Now, the building blocks itself could be very complex. I mean, I showed you some nanotubes, for example, but here is an example where you have a wire that is synthesized with gold on one side and carbon on the other. So you can make these type of structures. There are various techniques, template-based approaches that you can use to do this. And it's interesting, once you have these type of structures, you can play around with them. Right. So what we did in this case is we took these biphasic wires, which has got two components, and then dispersed them into a mixture of water and oil. And you can see, just like the micellar assembly, which is very common in chemistry, these things assemble with certain orientations because of the hydrophobic, hydrophilic interactions. And you can also switch these assemblies. You can go from a golden sphere, gold outside, to a black sphere because the carbon is outside now. So again, some of these concepts are very interesting, right? You could think about creating this dynamic kind of assemblies of structures that would be used for drug delivery. For example, I can encapsulate drugs in some of these capsules, and then target this to a particular area, and then by some stimulus, I can decouple them. I can reverse assemble them so that the drug is released. So again, people play around with the design of building blocks and the assemblies so that some of these dynamic events could be orchestrated. Again, we can also think about building entire devices on a single wire. I'll just show you one example. This is actually, and again, this leads to structures like this. So what we are trying to do here is build a battery on a single nanowire. So a battery needs a cathode, anode, and electrolyte, and some current collectors. So by nanoscale design and nanoscale engineering, we were able to essentially build all the components, anode, cathode, and electrolyte, in a single nanowire. And that battery, nano battery, actually performs, that works, and it cycles. So I think that there are lots of fabulous engineering marvels that you can do at the nanoscale. And again, unfortunately, I don't have the time. We do a lot of work on batteries and supercapacitors in our lab. And one concept that we came up with, shown in the slide, is what is called a paintable battery. The idea is that you can essentially make inks of all the components of the electrolyte. We spray paint them to make a battery. So you can make them in shapes, different form factors. You can, even paint a battery on your wrist if you want. So I think, the material science and nano engineering people have done all kinds of innovative ideas that would completely change the way future technology looks. I mean, for example, electric vehicles are becoming now very, very popular, right? But the traditional way of thinking about a battery is to think about a block of battery sitting somewhere in the car, right? But if you are able to deconvolute this whole idea and be able to spray your battery, then you can actually use the paint that you coat on a car or any vehicle as a battery, right? Again, I already mentioned about structure power. So a lot of interesting engineering innovations are emerging. You probably have, some of you have at least seen maybe the Samsung, next generation Samsung cell phone. You can fold it completely. You can actually roll it and put it in your pocket. And the only thing that is not rollable there is a battery part. So I think, our society has been really benefited by technology. There's no question. Not only that our society has benefited, but I think our lives have changed because of technology, right? The way we live, the way I lived 40 years ago when I was a student in Christ College is not the way people live today, right? So I think these changes have essentially come from the technology and the science that goes behind it, of course, right? So one thing we have to be, at least thank ourselves is that the people who are working hard. And again, I believe that in science and technology, there are no real heroes. It's all the cumulative work that people do all over the place come together. I think we have to be really thankful to those people who have really made our life much easier and much more. I will again, let me see what, it's almost 10 o'clock for you, right? So let me skip a few things and maybe come to one last thing that I wanted to mention. And that is really this graphene and single atom thick material. Again, the reason why I want to show this is you've really come to the limit of how fine structures you can make. If you're able to make a single atom thick material, there is no more, thickness you can go to, right? That's the end of the road, basically. That's the thinnest you can ever make, single atom thick, right? So graphene was a very fascinating discovery, and obviously it won the Nobel Prize because people were able to demonstrate that you can make materials, large area materials that are only single atom thick. And not only that, you can make devices out of them. You can play around with those things. So that was really an incredible material science there in terms of being able to produce stable single atom. And this field has kind of exploded because people now later realize that it's not only graphene, but there are many other materials that have these layered structure. You can extract single atom thick layers from many of these things. Even Richard Feynman was fascinated by this whole idea of layered materials. Well, there are many layered materials. The simplest example would be clay that you can find. These are complex oxides, which are again put together by van der Waals forces. So the point that Feynman was interested in is if you have a layered system, and of course in the layered system, the interlayer forces are not very strong, so you can easily pull them out, right, layer by layer. So if you can do that, then you can repack these layers in various configurations to make entirely new artificial kind of structures. So it's like, taking a few deck of cards and then shuffling and then putting them together, right? So you can mix and match the colors in these packs so that the shuffle becomes quite interesting. So again, if you can do this at the atomic scale, then the whole game becomes quite different. So again, the long-term perspective for people like us who are working in this area is to be able to create interesting device architectures, interesting structures by this mix and match approach. How do I shuffle these layers, atomic layers, and then put them together, and what kind of electronic properties do you get? Physical behavior can you expect? So there is a whole large number of researchers around the world trying to figure out how these new materials could be derived, what kind of properties they have, how do you control single atoms in these materials? How do you control defects? How do I control single photon emission? Because you can control defects. So there are all kinds of interesting quantum phenomena that appears in these type of super thin single atom material, and that's something that we have been working on. Again, not only that, you can shuffle these stacks and put one on top of the other, but you can also create engineered domains within a single layer. So what you are seeing here is actually by lithography and different multi-step process, we are able to take a single atom thick layer and engineer that layer to create other kinds of domains within that layer. So, I can create, for example, a sensor or an antenna on a single atomic layer. So again, that really brings us to the limit of how small you can go. As I said, you cannot go beyond a single atom. So that's really the whole idea, that in the future, as things get more and more miniaturized, these type of materials will become. I wanted to show one more image. It kind of, again, picks up a major advance that is happening. And that is related to the imaging part of things. I already said that metrology is very important. But to really understand, if you're thinking about single atom layers, if you're thinking about single atoms, then you need to see them, right? You need to figure out, what if I take their single atom and put it in a different place in the lattice? How does that behavior change? First of all, you have to image them. Secondly, you need to understand the property of these single atoms. So here is an image. It's actually, electron microscopy has gone through multiple stages of revolution in the past 10 years. And today, you can not only see a single atom, you can image a single atom, but you can also see what atom that is, right? Using energy filtered imaging, you can tell, okay, this is going to be tungsten, this is going to be molybdenum. So I just showed, this is an image that is taken in one of the bigger microscopes here. And this is a single atomically thin layer, but it has got 4 different components. It has got tungsten, molybdenum, sulfur, and selenium. And you can see, it's color coded. The distribution of atoms is now clearly picked up by the microscope. So what I'm trying to say is that you can see every atom in this structure and where they sit, if there is any defect, and so on and so forth. So along with all the synthesis and devices that you make, it's also important to have instrumentation that characterizes at this scale so that you have a proper correlation between structure and then there are quantum dots. Again, I don't want to go into detail, but some of these quantum dots are very useful in technologies like CO2 reduction. Another major technology that is important today is the whole idea of CO2 capture, carbon dioxide capture and conversion to some fuels. So again, like many people, we are also looking at some catalysis, some catalytic materials that might allow simple and straightforward reduction of fuels like methanol. So again, another important technology that is important for society in general because of the environmental effects of CO2. So that's pretty much all the examples that I wanted to give. I have just 1 or 2 more slides. And one shows the evolution of nanotechnology. And this is part of a study that I headed with the NSF, National Science Foundation, a few years ago. It actually shows the various stages of nanotechnology. So, nanotechnology as a discipline or as a big thrust came in the late 90s and early 2000s. And there was actually a bill introduced in the US Congress that set aside money for nano initiative. Similar to India, I think India also had a nano mission. So the first 10 years up to 2010, 2015 was these creation of materials, synthesis of nanostructures. The second phase of this that lasts maybe 2020, 2025 is how these structures get integrated into devices. And then finally, it's a technology divergence, which means that many of these applications, which includes nanotechnology, will see commercialization and major impact in the in future technologies. And future is going to be very interesting, right? There's going to be sensors everywhere, things that interact with you. I mean, this is an example I thought was in journals. I mean, this is a toilet that you can find in Japan. You sit there. Basically, because of large number of sensors, it gives you all the readings of your health. Basically a health monitoring system. Similarly, I mean, you can see today's cars, right? The sensors all over the place. So when you back out and you're going to hit another car, it'll tell you that this is going to be the case. There's going to be self-driving cars, right? Because you can essentially read out using large number of sensors what is happening all around you and provide that information back to you. And again, to be completely foolproof, you might want to probably use artificial intelligence to make sure that you're not really making a mistake. So, and again, many of these technologies, sensors and electronic devices need this continuous miniaturization because you wanted to pack more and more stuff in a small area. And that is where nanotechnology comes in, right? I mean, of course, there are other reasons why nanotechnology is interesting because the fundamental physics can also change when things are at small scale. But in terms of really technology implementation, the miniaturization really drives in a large way. So let me kind of end here by saying, taking a quote from Gandhi, saying that in a gentle way, you can shake the world. And that is very true, particularly when you talk about small things that we have been working on. And of course, all these things are possible because we get funding and a large number of people involved, students from many countries, including several from India. So, I mean, these days there are, also programs that allow students to apply for fellowships as well. So we have a good mix of people all over the place, many countries, and research makes it all the more worthwhile for them to be together because you can speak languages and talk different cultures. And that's how things work in the United States, at least in big research labs. So thank you very much. I think I went over time, but I hope you got something out of this talk. Again, it was a broad talk and I was just giving you more examples. There are a lot of resources available if someone is interested in nanotechnology. There are many free courses. And if you need any specific advice, you can always email me, or you can talk to folks. I'm sure that there is your faculty will be able to help you to some extent. But again, it was a pleasure talking, and I hope we will connect. And as I said, I'll certainly stop by and say hello next time I'm in Kerala. Thank you very much.
Thank you, sir. Thank you, sir. Thank you very much for your very wonderful exposition of the field of nanotechnology. Thank you. Now we have a few questions, one or two questions. Okay. One of our participants is asking. Please comment use of inorganic, organic, hybrid nanostructures for the development of energy storage materials. Use of inorganic, organic.
So, right. Again, it's interesting question, and the answer is probably more complex. But I can say that there are many different material systems that include organic and inorganic materials. I mean, for example, in our own lab, we use a lot of organic material for electrodes and composites that includes organic and inorganic systems for different parts of batteries. Of course, the most exciting stuff these days is the organic inorganic perovskite solar cells. So again, I think the is that organics offer you some advantages, right? Lightweight, cheap, and inorganic has definitely some advantages. It's higher efficiency, but at the same time, they could be not very environmental friendly. So creating these hybrid structures would certainly alleviate some of those challenges. One of the major problems with the organics was the lack of, the lower efficiencies, like in the solar cells. And that's why they moved from the organic solar cells to more the hybrid, inorganic, organic. And that seems to work very well. So there are lots of opportunities. And again, maybe we don't have the real time to go into details of different systems. But yeah, that's an emerging area. That's an exciting area. I would definitely pursue it if somebody has interest in it.
Another question is how nanotubes are incorporated in biology, particularly in proteins.
So that's again a loaded question because there are multiple aspects. People have been using nanotubes for various things, including some level of drug delivery. You can, for example, pack certain elements into nanotube and send it into your body and then release it using some kind of radiation. The other opportunity that we have pursued some years ago was to target nanotubes and similar nanostructures to tumors, and then by phototherapy you can heat it locally and create some kind of therapeutics. There are maybe other catalytic effects that you can use, imaging, and so on and so forth. But there is another aspect of all these things, and especially when you're using nanomaterials in biology, and that is the toxicity issues. So nanotubes, for example, there has been lots of studies, and there's more needs to be done to make sure that some of the things that you might put into your body is not dangerous for you. So, there are many agencies, including some NIH and NIOSH here, and there are many other European agencies as well, trying to look systematically at some of these materials and how they are good or bad for your health. So on the one hand, it might be very interesting material to actually do biological applications, but on the other hand, one has to be very careful and be choosy about what you can use.
One more question, sir, is there any safety issues faced in the field of nanotechnology? And
so I just answer that question, right? Obviously, it's like any other chemical, right? If somebody invents a new chemical or somebody invents a new vaccine, right? The reason why, let me talk about vaccine because that is so relevant now. The reason why people go through trials, animal trials and human trials and so on and so forth, is to make sure that this is safe for us, right? So it's very similar when a new material is created and you're afraid that the material might interface with biological systems like us. One has to be, very sure. So tests have to be done. I think systematic studies have to be done to make sure that, this is very much a safe material to use. And there will be, safety protocols. If you buy a chemical from a company, you certainly have your safety sheets that tells, this can be used to certain concentration, this should not be left open, so on and so forth. So I think for nanomaterials also, they're developing these type of protocols that you can use.
Thank you, sir. For the participants, we have the feedback form in the chat box. You may fill that feedback form to get the certificates. Okay, now I invite my Vice Principal and HOD of Physics, Dr. K.Y. Shaju, for proposing vote of thanks.
Hi, hello to everybody. Respected Aayan M Pulickel sir, today's resource person and very famous alumni of Christ College Irinjalakuda, and respected principal Father Dr. Jolie Andrews and Sri Jason Parekadan and Dr. Sudhir Sebastian and other office bearers of the Alumni Association and all other faculties and the participants of this webinar. So before saying vote of thanks, I would like to say a story of sweet revenge. See, I did my PhD in Cochin University. So this story happened in 5 or 6 years ago. One day a call came to me, a telephone call. They want Aayan Pulickel sir's contact number. So I asked why you are asking me. Then the call was from Cochin University, the physics department, and from a research scholar, maybe asked by some of the faculties there. So that research scholar told me, Dr. Aayan Pulickel is your alumni. So please give his contact number. So I searched for the number. Even the website I have searched, but I could not get any contact number. So I asked many teachers. So they were also not aware. So I asked to start the retired teaching members. And finally I got some idea about Aayan sir's residence, and that was at Kodungalur. By the time I was little ashamed because we, after teaching for some 25 years and not aware of our one of the famous alumni, I was little ashamed. But luckily, I found that the research scholar who asked me about Dr. Aayan, he was also from Kodungalur. So that was a blessing for me. So I revenged him that he is from Kodungalur itself. So you find out his contact number. So that is how I paid back him. So finally, he went to Aayan sir's house and gave me the details. And after that, we searched Aayan sir's photo and we put that photo in our seminar hall, which is the Hall of Fame.
Thank you.
So that's how the story went. Now let me come to my duty. So today we have got a even though we have attended many talks about nanotechnology, it was a wonderful experience to hear from the original, means the host mouth, the original means first few persons who initiated this nanotechnology. And I think the father of nanotechnology was Richard Feynman, who only through one sentence he predicted the scope of nanotechnology. He said there is a plenty of room at the bottom. So I think that the only sentence, Feynman became the father of nanotechnology. And even at our younger age, all the children will wonder the leaf of one, what we say, in our Malayalam we say chembe ila. So that leaf is, the water is not sticking to that leaf, while all other leaves are slightly partially wetting. One of the chamber leaf that is not wetting with the water. So every children will usually wonder why it is like that. So finally, I heard that that is also one of the due to the nanotechnology. So anyhow, I take this opportunity to thank Dr. Aayan Pulickel for his wonderful presentation, and hope we will continue the association with the Christ College in future. And on behalf of the Christ College Irinalakuda and the management, and also on behalf of the Alumni Association, And also on behalf of the participants, I extend wholehearted thanks to Dr. Aayan M Pulickel. Thank you,
Thank
sir.
you. Thank you very much.
Now I have to, okay, thank you, sir. Welcome, sir. Now I have to thank our principal, Dr. Father Jolie Andrews, who is continuously compelling all the sections of the college to conduct webinars in the background of COVID-19. Since regular classes are not taking place, we have depending on the online methods. So there is again plenty of room for these webinars. So Father is taking initiative to conduct various types of webinars, and one more webinar is coming from physics department on August 3rd about the supercapacitors, and another on August 13 on exoplanets. And I thank our father, Principal Dr. Jolie Andrews, for all the support given to the Alumni Association and especially to the college. Thank you, Father.
Thank you so much. Thank you.
Now,
Thank you.
Thank you, sir.
now
Thank you, Ajay,
I
sir.
Now I take this opportunity to thank the office bearers of Alumni Association, Dr. Jason Parakadan, Vice President, and Secretary Dr. Sudhir Sebastian, and all other office bearers of Alumni Association. Recently we found that the Christ College is lacking the strong bond between the alumni, and we decided to expand the Alumni Association, and Dr. Sudhir Sebastian is taking keen interest in expanding the Alumni Association. And on behalf of all of these participants in the seminar, I thank the organizers of the seminar, especially Dr. Sudhir Sebastian. Thank you, sir. And I also thank Dr. Joy VT, the HOD of chemistry, who is also a part of, has a role in organizing this seminar. Joy sir is also having wonderful research outputs and had applied some patents. Thank you, Joy sir. Now I have to thank all the participants. Now I have seen that more than 250 participants were active in the listening to this webinar. And on behalf of Christ College Autonomous Irinyalakuda, I thank all the participants of this webinar. And once again, I thank you each and everybody. Thank you very much.
Okay, thank you everybody. Thank you, sir.
Thank you.
Jatin, sir.
Then see you then. Bye bye.
Okay, see you. Bye bye.
Yeah.
And for the participants, okay, this is being recorded, and the recorded version will be uploaded in Christ College YouTube channel. You can watch it there. Okay, thank you for your support. Thank you. Thank you all. Thank you.
Thank you so much. Thank you, Sudhir sir. Thank you, everyone.
Thank you.
It
Thank
was
you.
a wonderful experience. Thank you, Joy sir,
Thank you.
Keveshai sir, Jason Parakadan, and our Josat and everyone. This was a very, really enlightening experience. So, wonderful. Thank you so much.
Thank you. Thank you.
Thank you.